We're going to move on to chapter 10. So we started the idea of hypothesis testing in chapter 9. That will continue on for the rest of the semester. Remember, we're looking at inferential statistics moving forward. So we had things like confidence intervals, and we had things like the hypothesis testing. So far in chapter 9, we looked at one samples. What we had is we had this one population. From that population, we collected a sample, and we tried to figure out, is that sample really different from the larger population that it comes from? But now in this case, we're going to be looking at two distinct populations, at least for the first few sections. So we're going to be comparing the results of two different groups. So some notation that we're going to use is that we're going to use subscripts to indicate those in the first group versus the second group. You could also, sometimes there might be, say, A's and B's. As long as you keep all of them the same and you understand which group corresponds to which one, you're good. But there's going to be two sample means, right? A sample mean from one group, sample mean from the other group. Okay, so we're going to use that notation. So to understand kind of how we're going to do the hypothesis testing, first thing we want to note here is that the difference in the means of two independent samples is normally distributed when both population standard deviations are known. So similar to a single sample, if we have a known population standard deviation, then those sample means form a normal distribution. So you have a known population standard deviation, you have these z's that appear. So we have x sub 1 minus x sub 2, both these bars. The difference in our sample means is approximately normally distributed, where the mean is mu sub 1 minus mu sub 2, and then the standard deviation is the square root of sigma sub 1 squared divided by n sub 1 plus sigma sub 2 squared divided by n sub 2. Then the z-score slash test statistic, because as you saw on the videos before this last exam, really these z-scores do correspond to these test statistics, and these p-values correspond to being as extreme or more extreme than that. This is going to be what we find, is we find our z is equal to this. The difference in our sample means minus the difference in the population means divided by this standard deviation. Or in other words, we have our data value, which is the difference in means, minus the mean of this normal distribution divided by the standard deviation. Okay, so we know both population standard deviations of both those groups. We use this. However, if we don't know both population standard deviations, maybe both of them are unknown, or maybe one is known and one is unknown, the difference in the means of these two independent samples will require a t-distribution. So we do not have a normal distribution. We have to use our student t-distribution, which is exactly like what we saw before this last exam, was that known population standard deviation for means, we use these. If we have an unknown population standard deviation, we use these t's. But in both of these cases, there's a thing I want to point out. The samples are coming from distinct populations. So remember, we have these two distinct groups that we're studying from, and we're trying to compare them within these groups. It's not taking things from a larger population and taking a sample from it. There's two of these taking place. So the t-score slash test statistic, again, this is going to be very similar to what we have over here. We have our data value minus the mean divided by the standard deviation. But again, this is a little bit funnier because now we only have sample standard deviations available. So if you remember, one of the things that defines this t-distribution is the degrees of freedom. So in your homework, you had to answer, say, t sub 8. If there was 8 degrees of freedom, that is the type of distribution we were using. So remember the rule for the degrees of freedom, when we had one sample, it was n minus 1. So now if we have two samples, well, you should think, well, what do we think the degrees of freedom might be, right? So you can scream at your computer right now what you think it'll be, and indeed, the correct answer, as you all thought, it is going to be S sub, my marker died. It is going to be S sub 1 squared divided by n sub 1 plus S sub 2 quantity squared divided by n sub 2 quantity squared. All of that will then be divided by 1 over n sub 1 minus 1 times s sub 1 squared divided by n sub 1, that quantity squared, plus 1 divided by n sub 2 minus 1 times s sub 2 squared divided by n sub 2, that quantity squared. So that is your degrees of freedom when you have two samples. It gets me every time. It really does. So fortunately, we will not be doing that by hand. The calculator will take care of this because that is nasty. So, but what that means is that you have now a really weird type of distribution. Now you might have T sub 13.78 or something. So what your degrees of freedom now will no longer always be a nice integer. So these are the first two sections in chapter 10. We will go through some videos of doing some practice problems to understand how do we structure hypothesis testing for these two samples with either we're looking at means in both of these. Either we know both population standard deviations or we don't know both population standard deviations.